So consider the following R module homomorphism. So this is exact. If you have this sequence like this, all these phi 0, phi 1, phi 2 are homomorphisms, and these m1, m2 are some modules. So this is exact at a particular module mi if the image of the map coming inside is equal to the kernel of the map going out. So it is exact at say m2 if image of the map coming in phi 1 is equal to kernel of the map going out. So kernel is phi 2. So more pictorially you can see like this. So say you have mi here and this mi looks like this. So in mi there is a image of the previous module sitting. So this previous module here, this gets mapped inside mi. So say it gets mapped like this. So this mi minus 1 sits like this inside mi. So this is the image. So this is the map phi I minus 1. So phi I minus 1 is going out of mi minus 1. And this is the map. So this entire thing is the map. So this is the image. So now when you apply phi I to it, this entire thing becomes 0. This becomes 0. So this is the kernel. So if you take pre-image of 0, this is the kernel, and this kernel is precisely the image of the previous module mi minus 1. So this is mi minus 1 sitting in here, and this becomes the kernel. Now let us see some examples. So say you have this map like this, 0 to m1, and then you apply the map var phi, you get m2. So this is exact if and only if kernel of this var phi is 0. So why is this true? So notice that this kernel has to be equal to the image. So the image here is just 0 because you just have 0. So this is exact if and only if kernel of phi is 0. So that means this map is injective. So every time you see a 0 on the left side, you make your map injective immediately. Now the second example is, so you have this map like this. So this is exact if and only if image of var phi is equal to m2. So image of var phi is equal to the kernel, but here entire m2 is getting mapped to 0. So this entire thing is the kernel. So this is the kernel. So image of phi is equal to m2. So that means this map is onto. So every time you see 0 coming on the right side for exact maps, you make this map onto. Then you have zeros on both sides. So if you have zeros on both sides of var phi, then you know from here and here you have injection right here, and then you have surjectivity also. So injection comes from here and surjectivity comes from here. So this is both injective and surjective, so therefore this var phi is iso. So this map is exact if and only if this var phi is iso. So in general you have a short exact sequence like this. So this is what a short exact sequence looks like. And now we already know that you have a 0 on the left side, so this phi 1 has to be injective, and since you have a 0 on the right side, this phi 2 has to be surjective. So this is exact, the sequence is exact if and only if this var phi 1 is injective and this var phi 2 is surjective. So consider this map of modules. You have a module homomorphism from A to B. So this yields a few short exact sequence. So first case is, say A is a submodule of B. So A automatically injects into B. So you have 0, A, B. So there is a natural injection, and then you can modulo out A. So this will become surjection. So you have a short exact sequence. So right now we are trying to use this short exact sequence. Give examples of short exact sequence. Now in case A is not a submodule of B, then you can always put kernel of phi. So you put kernel of phi, so this will naturally be injective, and then you have a surjective map which is just image of phi. So you again have a short exact sequence. So rather than considering A, you can consider B. So in B you will obviously have injective map which is image of phi, and then you can modulo out B over image of phi to get a surjective map here. So you get another short exact sequence. So now let us consider gluing and splitting of these exact sequences. So say you have this exact sequence like this. You have M1, M2, G, and then goes to 0, and then 0, G, M3, this phi3, M4. So now if you have something like this, you have this G and G common here. So G on the right side here and G on the left side here. Then you can glue them together. So if you can glue them together, you can glue these G's together, and you will get this sequence M1, M2, and then this phi2 will go all the way to M3, phi3, and M4. So why does this hold? You can check here, right here. So we have to check here at M3 that this thing should hold. For exactness at M3, you need this kernel of phi3 has to be equal to image of the map coming in, and image of the map coming in is phi2. So this we have to show. So this you have to show. So what is image of phi2? So you see that 0 is here on the right side, so this map has to be onto. So this is precisely image of phi2. And here you have this map is injective. So if this is injective, so this G sits completely inside M3. So this is G which is sitting inside M3. Now as you can see from this diagram, this will get mapped to 0. This G is going to get mapped to 0. So G is injective, it sits inside here, it gets mapped to 0. So this G is precisely kernel of phi3. So you have G here and you have G here. So if you're given something like this, you can go into this long exact sequence. If you're given this long exact sequence, you can split it like this. You have G, which will be image of phi2 here, and kernel of phi3 here. So you have this 1-to-1 correspondence. So instead of this sequence, you can split it like this: 0 to M3, and you modulo out your image of phi2, which is precisely G. And then you can inject this into the next map, which is M4, and so on. You keep image of phi2 here, but you can do M4 here. Now you can split it like this also. Now the advantage of this is that you do not have to consider this M3 again. Sometimes it's better to modulo out by the image of the map. So you can generally write it as co-kernel of phi2 here. So this is the same thing as you have here. Now if you had something like this, then it means that we are talking about this region outside it. Now if you're just talking about this region outside it, this region obviously you can have this will inject into this. Now the advantage of this is that sometimes in computations of homology or cohomology long exact sequence, you need to modulo out by certain images. So depending upon the context, you can use this. Now coming back to here, you have G and G here. So this G and G helps us glue the two sequences together. So you have this image of phi here, image of phi here. So you consider this as G and consider this as G. So since these two are the same, now you can glue this. So you get a long exact sequence like this. So again, this is the same homomorphism here. So this homomorphism yields to another sequence like this.